Okay, let's start with this new day of review. Alone again, but okay. I'll review also part of the things that I reviewed in the previous review because I was running, trying to do everything, and was not so great on the proceeding. And so I wanted to explain a little bit again something about the mechanical statistical part, Fermi, Dirac, and Bose-Einstein. Those are, I want to be quite clear. As you see, okay, as you already said, the statistical, the quantistic statistical distribution. One is the Fermi-Dirac. They are the one for the fermions. They are a particle with antisymmetric function and with alpha integer spin. That is this characteristic intrinsic angular magnetic momentum of the particle. It's something that is not exactly that the particle is spinning, but is intrinsic. But it is because something I want to clarify that is this part is mechanical statistics done for this course, is not general. It's, we consider just usually the cases that we are interested into. So some is not perfectly detailed, is not something we have to study in deeply mechanical statistics. We just want to clarify something for our use, not for every physical cases we use. The particle of Fermi-Dirac are called fermions. Obvious. It's GI. It's this one is the generation of energetic level. Not exactly the state. Someone clarify, but it's just how many particles you can have with the same energy. And here the Fermi-Dirac make the difference because the principle of exclusion of Pauli clarified that you cannot have more a certain number of particles for each energetic level. So you cannot have essentially because the statistics say that you cannot have two particles with exactly same quantic number. And since usually we have several quantic numbers, there are at least 3 or 4, I don't remember. One is n, that is the number that determines the energetic level. Then there is the one that determines the momentum, angular momentum, L. The last one that is not connected, that change a little the energy, is the spin number. So usually it's referred just to this one, because the other can be the same, and you can have just particles with spin 1/2 or minus 1/2. So you can have just two. Say that you can just have two particles for each level. Actually, it's a little more. For example, in atomic orbital, you can have several electrons for each energetic level, but it has a subtle difference actually, because they are going to change something slightly, especially in the interaction among particles. And at the end, what changes actually is the spin. So we consider the generality of John. We have circulated, we have this famous formula that show us exactly one thing, that if you consider the occupation factor function or occupation factor, that is n divided by g, the number of particles in a certain state, and I divided by total number of state with that energy level, it's this number is 1 divided 1 plus a positive number. That means that below is number that is always greater than 1. That means that this number it essentially is the limit, square limit is 1. It can go to almost 0, but is never going up there. It is a clear difference with the other. In fact, if you consider the classical limit, we are going to absolute 0. So temperature goes to 0. We have this distribution, rectangular distribution. That is 0 up to a certain value, then or higher, in this way. Let's open the annotation. In the limit, we have this characteristic for energy higher than Fermi energy, as we can, this actually should be an F. We have no particle, and before is completely killed. This is the n divided by g. It is easier. You don't have to know exactly how g grows. This changes everything, because you can see that you cannot, you have this quantity that is increasing up to here. So this shape is not dependent on temperature. Just the number of particles, because you have here that number of particles, another, and so on, depending on the G, and so you fill up to a certain value, that is epsilon, the Fermi energy. So how much the average energy of the state is not depending on the temperature, but just on this value, Fermi energy. But okay. You say we have the no. The formula with the three Lagrange multiplicator 1 for the probability, eta for the number of particles, and beta for the energy. So in fact, you have this connection. This is here. You can rewrite the eta, also because in this case eta is less than 0. And you can rewrite the equation in this way. It is definitely a little clearer, the connection about energy of the level of the E level of the E and this limit. As I said, the Fermi energy is connected with the number. In fact, it's connected with the Lagrange multiplicator that is put for the limit of the number of particles. So we can calculate based on the number. In this way, you can have a nice formula. This is the generic. Formula, you not complicated, simple to calculate, but if you use this approximation, it's easier and you can obtain the result in this way. Where you can see definitely the Fermi energy is dependent on the number of the density, numerical density of the particle and the mass of the particle. That's dependent on that. So the total internal energy for T that is going to absolute 0, because this is the only case when you can have the effect of the total degeneracy. That is called when you have this situation. You have this relation. The total energy depends on the total number of particles to the 5 term. I think here you can have the approximation for Fermi energy in general, and considering peculiar with some value density in unit of 10 to the 6 grams per cubic centimeter, and the mass of the particle in mass of the electron. And this also, you can see that this energy is approximate for this density or little less than 1 megaelectron for an electron. And but if you consider protons, neutrons, they are 2 times more massive. This value definitely drops. Then you can see what is called the Fermi temperature. That is simply the energy, the temperature you need to have a mean energy per particle of around Fermi energy. That means the Fermi energy divided by the Boltzmann constant. That is, in this case, for electron, and this density is 2-3 billions of Kelvin, and you need a lot of energy. Then the other one, as Bose-Einstein, that is not only there is not the Pauli principle, exclusion principle Pauli, and that are for bosons that are particles with symmetric autofunction and integer speed. They are the same, you have this approximation. In this case, okay, here you can see if t goes to 0, you have this distribution, eta minus 1. As said, we are not interested into all the boson. Essentially, the only boson we have to deal with in astrophysics mainly are photons, because other boson can be phonons. In our case, stellar structure evolution, we are not so interested. Atomic nuclei with an even number of as a mass number to start to behave like bosons. Typically, we need situations that are not in our regime. So we just consider photons where the number are not conserved, so we can put eta equal to 0 and take away the eta. This means also that you see that this go to 0. This is 1 minus 1. This is something we have by 0. That means that for temperature to 0, this number skyrocket directly. T should be unequal actually. This should be the equal. Okay. Here it's the calculation. Here it is the delta n, the density. And we have the calculation. This is not exactly the Planck, because here we are already integrated in all the angle, and we are considering, you can see this is density, not by surface. This is not a flux, like the Planck law. In fact, here in Planck law, this is the c square, not cubic on the c, and because for to calculate the energy. This is the classical, then goes to the Stefan-Boltzmann relation, the total energy for gas of photons, and the total energy that is multiply T for the 4. Okay. Here was most want to go, because well, actually this is the general. This is say the C plus 1 Fermi-Dirac, that brings the fact that it is always 1 or little greater. Minus 1 was Einstein. That means if this is equal to 0, this the exponential minus 1 can be approximated with just this argument. And then 0 and Maxwell. Actually, and to say that Maxwell-Boltzmann technically is an ideal gas statistics. That means that it's not physical. There is no real gas, physical gas that goes by the Maxwell-Boltzmann. But it's a good approximation usually for classical regime. Usually, actually, the should be used Fermi-Dirac and Bose-Einstein, but for normal condition, temperature, and density, these two are approximated by this one. This is because usually the value of the exponential is For normal gas, it's really positive, so this means that this exponential is bigger than gas minus 1. It can be ignored and goes to the Maxwell Boltzmann. It said what is the instrument, the numerical density, and that this can be integrated. This is in approximation. It technically should be a sum, not an integral. Integral means continuity that is not perfect, but with some approximation we can go there. Especially we have a lot of number of particles, usually solid gas. This is the tail, and what we are interested more in the occupation factor, occupation function, index, and so on. The eta is the generosity parameter that is connected with the degeneracy, and here just a correction, because if the eta is really positive, greater than positive, we are going in the situation of Maxwell-Boltzmann statistics. No, is not exactly true. There is no degeneration. The degeneracy is there. Actually, it's the Maxwell-Boltzmann statistic is the one with the highest degeneracy, and for this reason, we have no degeneracy effect, because the degeneracy. We talk about the degeneracy and effect of the degeneracy when the degeneracy are limiting the number of particles. Like in Fermi graph, you cannot have more two particles due to the spin. You cannot have particles with the same set of quantum number. So you have a limit on the number in each level, energetic level. In Maxwell-Boltzmann, there is not this limit. So the degeneracy of the level is high. That is usually the gas ideal, but the limit is not actually infinite, but depends on the energy, varies with the condition. In this approximation of continuity, essentially the G goes more or less with the square root of the energy. And you can approximate in this way. In fact, it's common to see more the Maxwell-Boltzmann statistics and Maxwell-Boltzmann distribution. That is the statistic applied to the velocity, to the speed, and with the classical this distribution that vary with, I don't remember exactly what were this value, but anyway, this with temperature, this is a lower temperature, higher temperature, the area below is always the same, is the number of particles, the distribution with the velocity change as known. So we have lower temperature, we have really well packed particle with the same lot of particles with the same energy, let's say energy, so at the same energy level, and then this broad. But there is always particle at lower and higher energy, and we have increasing lower and lower number of particles for each level. So the density for each level has to be really low. That means that these have to be really big, and then the classical we see value have to be less important. This is also another reason why we usually for this regime we use Maxwell-Boltzmann. In the here theta partial degeneration, actually in the case usually boson have infinite degeneration. You can put how much part we want for each state. Essentially, is not to see the effect of the energy, but you have the effect because are quantistic particles, so you have this this deviation because the effect. But usually it's more or less the same. The Maxwell-Boltzmann doesn't change a lot, but at really low temperature we have what is the famous now. We have talked about condensate, Bose-Einstein condensate, that is peculiar when all the particles are managed to stay in the ground energetic level and behave like just one particle behaving all together. But it's not our interest because we cannot have this kind of state of matter in the stars. What is more interesting for us, this is usually interesting more for the behavior of the photons in thermodynamic equilibrium, because we got the Planck law. And here we have the degeneracy, strong degeneracy for Fermi-Dirac particles, electrons, principally. And usually when not exactly, in general, physically when temperature is really low. In this case, when the density is very high, so we have a high Fermi energy, and so the temperature is small respect to the Fermi temperature. Yeah, as I explained before, if I consider perfectly and theta is greater, I'm going to the Maxwell-Boltzmann. If it's really small, we have the behavior of the Fermi-Dirac. And also this behavior, as shown here, for Maxwell-Boltzmann, here is the n divided by g, equation factor. So since exponential at 0 goes to 1, then goes down. Here the Bose-Einstein then goes higher and higher because it's remember here we have the -1, so at beta that is an energy that is really small, but when this is small it is small, this goes to the argument. In this case, there is no this part. There is just the energy. So it's going increases like 1 divided by the energy. And for Fermi-Dirac has this different behavior. They start to fill in up to the energy value and thing. And this is also the limit, because when you start to see it, when this energy is definitely higher than typical and thermal energy of the gas. And everyday use of the Fermi Dirac is the metal, where inside the electrons are actually in Fermi Dirac regime. In fact, the Fermi energy is around 1 million Kelvin. So the electrons inside the metal are behaving like degenerate gas of electron. So we see are really well conducted, in fact. And why usually later in stars the density of the electron is high, but the temperature are definitely higher. So at the beginning the behavior is not helpful. Something that you have to remember, also important, is about Maxwell-Boltzmann. If you divide Maxwell-Boltzmann for two states, you have the ratio about the number of particles in one state divided on the other state. It's that is the ratio between among the degeneracy value of the two states, on the number of the particles can be in two states, multiplied by epsilon, minus beta, and the difference in energy among the two states. If you, that is really useful usually to check, you see if know the situation about the ground level, you see how much are the particle in the second, in the energy level just above the ground level, and the central temperature, you see the distribution. Right, yeah. Usually in statistical distribution, we have the number of particles, n, but in physics, usually we use to talk about gas, the numerical density, so we change dividing by the volume. It doesn't change a lot. Because G usually have inside the V, because here is the volume in the occupy in the phase space divided by the unit volume phase space, and you get the number with GD, the part the degeneracy, and you just divide by the volume, because you usually have talking about the density, what you need to measure, not the number of particles. And also you see here space, velocity, h. Remember about the conjugate variable and Heisenberg principle of uncertainties that we will see again. Then, okay, let's remember this part a little more quicker. The thermodynamic equilibrium, where each process are balanced statistically with this inverse. So we have radiation, we are ruled by the Planck law, that is the Bose-Einstein statistic. The gas, the matter, ruled by the Boltzmann, usually Maxwell-Boltzmann law. But the Boltzmann law and the Maxwell-Boltzmann statistic. And then interaction for gas radiation, interaction with the Kirchhoff law, that say about gas absorb, radiation absorbed or emitted in this equilibrium. these things, you can have the equation state that are important, because the equation state describe are these variable properties are connected: pressure, temperature, volume, and number of particles. Usually it's two together as density. As I said, usually in most classical mechanical statistics, we use the equation state with the number of moles and volume, but we prefer to change everything to have density of mass density and molecular mass, atomic mass. That is the mean mass in atomic unit that each particle has. It means that it's permitted if you multiply the metal density by this value, that is this is pure number, mu, that molecular mass, by the how is the atomic unit, you have the total density of the gas. All the previous was thinking that the particles are not interacting. That means that all energy is just the sum of the energy of the single particle. Not you have to consider interaction other energy like potential inside, and in this case, consider in the star usually internally it's above 10 to the 5 Kelvin. That is complete ionization or almost. So to have if you needed to consider interaction, you needed, that means the Coulomb energy must be comparable to internal energy. But if you do all the calculation, we see that normally the ratio among Coulomb energy, internal energy are really small, about a few percent, 1-2%. So it's almost negligible. So we can, so you say, so only planets you can have really high. This is because the mass is small, and this increase of smaller mass, you can, it's comparable. Otherwise, you can just consider in non-interacting particles. That not means the particles are not interacting. They are interacting with collision, but interacting only during the collision. There is a collision, and then they not see them. They arrive, they collide, and goes away. The collision helps to exchange energy to what is called thermalization, but then there is no more interaction. Just okay. So since we want to understand the equation state, we have to calculate the pressure. The pressure is just the collision of the particle in the surface. We consider the border of the gas. The pressure of this gas are doing what is outside is due to the movement of the particle to the collision. So it's important to understand what is the distribution of the momentum. We are here explain in detail how to calculate the flux. considering mechanism is usually not considering isotropic density. There is no difference among all the direction. With some trick, usually we have some difference. So considering this trick, mathematical trick, we can change and go to the value, isotropic value. We get the situation. And here we have the momentum, P and the V. It's true they are connected in this way, but this just when the velocity are not relativistic. So we need to stay here, and then we have the case for calculate non-relativistic gas will be equal mv in this value, and for relativistic gas, the relation among the two is a little different. So we have this other value. This change essentially this factor from 2/3 to 1/3 we saw from Weber's theorem, but this change completely everything. For photons, that is in this regime, we can put, because we have the pressure is equal 1/3 of UNV. UNV is the density of energy. It's this value, so we can calculate that the pressure variation is just 1/3 A T1.4 with A viscosity. And the internal energy by U the mass is this one divided by the density of the mass of the gas. And remember, in general, the pressure is the pressure of the ions, of the electrons, and the radiation. We can put together ion electrons to have the pressure of the gas, plus the pressure of radiation, and we call beta the ratio among the pressure of the gas and the total pressure. This is not the beta used in mechanical statistics. As said before, molecular weight, that is said that it's the, you can define it, it's the total mass of the gas divided the number of particles. So we have the mean weight divided the atomic unit. That means that molecular mass, molecular because it's the mass of mean mass of the molecule, but not molecule is just particle. It's called that way, and the mean weight, the mean mass of the particle using atomic unit. Considering the density is the sum among all the particles with their mass. And the numerical density, numerical density is sum to the total density and numerical density. We can define the fraction, mass fraction in this way for a certain particle. It is obviously 1 by definition. We put all these things here as we define the rho, density, total number, everything to have situation. Here with the AK is the mass number of the particle, and with the fraction mass fraction of the particle. This usually most used to define because you can have the composition of the stars in for each element this there are value and so put inside. In fact, you consider that the total number of particles is the number of electrons, ions, doing the calculation. Okay, I don't think you need a lot of to review here. And we can do some approximation. For electron, we have the 1 divided in molecular mass, usually the molecular mass express 1 divided in mu, it's always the denominator, is 1 plus x divided by 2. X is the fractional mass of the hydrogen, this typical value for the sun. Zeta, this is hydrogen, this is helium, and this all the other elements called the metals. For the ions is this one with the here an approximation that the mean value for the mass number of the particle. So that is quite big, so we can ignore this value. Then also one result is here that the molecular mass have to be summed by the inverse, not summed directly. So the general molecular mass for the gas will have this value. And for the sun, we see the pressure of the electrons are more or less equal to the pressure of the ions. One part that it is really important to understand, I stress again, about the degenerate gas. Usually say that the perfect degeneracy can be only be with absolute zero, absolute absolute temperature is zero. That, but is not possible. It is not physical, but it's impossible. But if you can find it at really high temperature, this is because it can happen also with a really high density. This is because with if you consider the value for each particle, so the opposite metal density, as this value is fixed essentially, to constant for the gas. It goes with the inverse of the density. So if you have really high density, you see that the space for one particle starts to be really small. And so if you consider the phase space, that is the space we're considering space in velocity, its speed, and the particles have to be really well localized in space. And then here starts to be the uncertainties principle that say that the space and speed, since they are two conjugated variable, their uncertainties, the product of the uncertainties cannot be smaller as we want. That essentially means that if you plot position against velocity speed, the certainties are of the location as an interval in each one, so the particles are in a certain square. You have the position by space and in speed. Yeah. Oops. Yeah. We can do it in better. And you have the position of the here as the link with this uncertainty in space, in position, and speed. Will tell that if you increase the certainty, you decrease the certainty in position. This means you have to increase the uncertainty in speed. The area inside of this area must be the same. But so you have the uncertainties are connected this way. So if you have a small density, can be rectangular, horizontal, the momentum of the particle has no limit because the certainty is quite small, so can go where you want. When you have a really high density, and certainly on the particle can be started bigger than what it should be, can scatter a lot. That means that in this way, particle can start to have value that different quite a lot from the value that are given by the temperature. And here is where we start the Fermi-Dirac to enter. This is because the statistical Fermi-Dirac start to impose is a reason, and so the particles start to have a momentum that is definitely bigger than the one given by the temperature. This is also when the energy, Fermi energy, start to be definitely bigger than the thermal energy, because in gas or fermions, always there is the two parts, the pressure imposed by the distribution and the one imposed by the temperature. But usually this uncertainty is so small that it doesn't matter. At a certain moment, this pressure starts to increase and be important. So it is the pressure that actually is influencing the gas. And essentially, what are as actually, you can just consider if you have a collision, we have thermalization. That means the particle arrive and can exchange any amount of energy up to the possible that the particle after the collision can have energy of each one of the energetic level with available space to go there. But when the degeneracy starts to show its effect, after limiting a lot, you have a collision, and maybe the only possible is just the two fermions shift their velocity, the energy, and not can redistribute. So since we are considering by quantistic, the fermions particle are not distinguishable. Essentially, the particle arrives and goes away identical, so there is no interaction, there is no exchange of energy. This limit also imposes that we saw the distribution of this rectangular shape. They are not more influenced by the temperature, but the density, because depend on the Fermi energy and not on the thermal energy. When you are total degeneracy, that usually never happen physically, but you can have a really high degeneracy. Total degeneracy, you calculate everything considering that t is equal to 0. You have this value, so the momentum goes by the numerical density to 1/3. Oops. This value for the electron. And you can see that can vary. And at the end, the pressure you see for non-relativistic gas, you have the situation. And for relativistic gas, you have this situation. Oh, okay, going here. There is something that I remember I want to show. Yeah. Here. These parts are showing quite well the reason why relativistic and non-relativistic is different, because usually for energy in relativistic gas, the energy is equal P per V divided by 2, or P to the square divided 2m. But if you are going to see relativistic, you need to use the relativistic value. So the energy is equal to this value. So the energy, Fermi energy for the system is equal in this way. You have to calculate the total energy using the with the reference to the Fermi momentum. And less rest energy, less mass, what is called. And you see in the approximation when the energy is quite higher than this value, you have the relativistic particle is P multiplied by C. It changed. Before the energy was connected P and V, P depending on V, so it's like quadratic with the velocity. Here it's just depending on the momentum, and so it's changing in different way, changing smaller. In fact, if you see later, for the relativistic gas, there is a limit mass that can sustain the pressure in the gas. Otherwise, could be the collapse because it's not viable. While the relativistic Fermi gas, there is no this limit. This is also because you can see here from relativistic gas is the density to the fifth term, so increase little less than 2 with the density, while for the relativistic gas is the fourth term, is less. That means for the relativistic gas, increasing the density, the pressure are increasing less. So if you compress a gas, you are increasing in its potential energy, so the potential effect start to be bigger. The force given by the pressure increase less, and this causes this limit. And you can see here when the better to show the right thing. The free distribution, Bose-Einstein, Maxwell, Fermi, that are, you see the Fermi-Dirac are the one with smaller distribution function. These things, I think it is actually the occupation function. And because it cannot put as much particle it wants, Bose-Einstein, there is no limit, can grow bigger. Maxwell Bose-Einstein usually have the limit of 1 at 0. Oh, okay, this. And here you can see definitely with the temperature of more or less the same energy that the Fermi energy, there is this behavior that seems quite similar to the Maxwell-Boltzmann. And you see here, it is in the classical regime, when the thermal energy starts to be definitely smaller, the Fermi energy, the classical energy, the limit, the quantistic effect and the energy start to be shown, and you have that this is because particles cannot have the energy they want. They just cannot go there. Here, since is plenty of space, collision here can put a particle here and a particle here, no problem. But here, if there is a collision, you cannot put a particle here because it's full, it's one. So just a small situation can go here or here, but here you need to distribute. So just a few interactions possible and are really well fixed. Essentially, all the particles stay with that movement can be really high. And here you see a situation when temperature goes down, essentially. The Fermi-Dirac feeling causes the generation, the difference, because these are the behavior of the Maxwell-Boltzmann classical gas, while and you see energy connected with the momentum, so goes down, so the momentum goes down, while here with the temperature that is going down, or in this case it is less than start to be smaller than the Fermi energy, the moment actually goes up, the opposite. You are, cannot cool actually a Fermi gas, because essentially that if the motion, the temperature is connected with the motion of the particle, you cannot cool down because the particle cannot cool, because that is not possible. I said you cannot have always perfect degeneration, never, because you have the electron, but you have also electron are not the only one. You have also the all the ions, and you see here they depend on the mass for non-relativistic. For not for relativistic particle, just depend on the molecular mass. Doesn't depend on the gas. Doesn't depend on the composition, but doesn't depend on the mass of the particle. The pressure, so should be the same, but to manage to have ions at the relativistic effect, okay, you need really high temperature. So usually doesn't matter. And also you to have high temperature, that means the first one could be the proton, so hydrogen nuclei. But if you have high temperature, usually all the hydrogen is already burned, already used, transforming helium. Helium is 2 protons, 2 neutrons. That means that the spin is integer, is not alt integer. So helium nuclei are bosons, are not fermions, so it doesn't degenerate as this one. But the helium can do a condensate, Bose-Einstein condensate, but it's in really low temperature, so it's not our case. You should need with atom with an even odd number of even mass number, but here the mass is really high. You cannot have this regime. In partial degeneration, you see here, so you have the mixed situation. You can write in the situation ideal gas with this correction, or generating gas with the correction of the temperature. So are not perfectly separated. That is the reason why you can start to increase the temperature when the thermal energy to be nearer and nearer to the Fermi energy due to the density. The equation states start to move from this approximation to more to this approximation, so the direction is lift or broken. And this just to show that in the case here, if the nu is the same of this new parameter, that you saw cause the degeneracy essentially. When it starts to be quite small, this value is almost 1, so you have the ideal gas regime, not more than. This is written often in Spanish, often in English. Okay. For radio fraction, here is this density of particle. This is why the reason is different from the Planck law. Should be c squared. And see, you can, as so before, you can calculate the pressure and this value. And essentially the interaction is that the radiation interact with the gas with the several way and goes up, leaving a little of momentum to the gas because it absorbed, emitted, or interacted with the scatter, and exchange of energy cause the creation of this pressure. So where we are? Okay. Another part of the gas in the adiabatic process, we have the interesting in see how vary the adiabatic exponent. The adiabatic process when there is no exchange of heat in the surrounding. And doing the calculation, we can have this situation when there is no change of heat, the pressure just changes with the density, similar to the degenerate gas. And we have this relation among the properties. Actually, in the adiabatic process, there is a connection between pressure and temperature, that is this value. It's not that the gas, it's just that we can express the pressure just as a function of density. So we have a relation among just with a constant among pressure and density, pressure and temperature, temperature and density. These two value, the coefficient. When they are equal among them, you have the adiabatic, they are also equal to the adiabatic coefficient. And the Canadian gas, this value is 5/3, or the radiation is 4/3. The adiabatic coefficient can vary because during ionization, part of the energy can be absorbed by ionization, so there is not behaving as usual because if you're compressing, expanding the gas can pass to thermal energy, as in case since the ionization are subtracting some energy, so we have energy goes from the internal energy to the ionization energy. There is a different behavior. We can calculate everything, considering the several parts, also because not we have the electron, the hydrogen atom, and hydrogen nuclei. This is the nuclei, and I ionized 1 times, and 0 on the ground level, that is neutral atom. So we have the particle and all the consideration, this thermal formula. The X is the number in state particle on the second level, because ground level is neutral, and Ny is the ionized, and the total number of particles quite similar to the, depending this you can obtain from the here you can see N0, N1, more from low is the ratio among G, different of the epsilon. Here we can see the G of the 0, 1, and you get this value. So ionization the ratio among the several levels depend on the pressure, on the temperature, energy, ionization energy. Here, there's a relation among internal energy, pressure, and ionization. Do the calculations before you get this complicated formula, because you have this relation among pressure and density, and you know for the adiabatic value process the certain this is the adiabatic coefficient, and this value will depend. And you see if it's no ionization or complete ionization, the adiabatic coefficient is the same for third classical of gas, because behave like a classical gas. And in the between can vary. So at certain point you have this usually half, you have this minimum, and it can be quite small. And yeah. Here you can see the adiabatic gradient is changing with here is a variation of the fraction of ionization for the hydrogen. It is just 1, so is increasing with the time with the pressure here, the amount of pressure, temperature, the amount of hydrogen ionized. For the helium, you have the 2 for the first ionization, second ionization. It is a classical study for the atmosphere, stellar atmosphere, that the line depends on this value, because obviously to have a line from helium as 1 time, so you need to have this element. So here, this actually temperature, you have the maximum, then you have not enough energy to have enough helium 2, or you have too much energy to have helium 2, you have helium 3. And here you see how this is changing with you have the drop increasing, then drop again, because this is the double transit. Here this goes down, increasing. That formula was just for the hydrogen. Here is both. So maybe a little bit. The radiation can be also changed. You have the pressure at this value, pressure of the gas, pressure of the radiation, internal energy from the radiation from the gas. Sorry, I shift. The change of Q is the equal of this one. Du here have go both value for temperature, then density, while for the pressure of the gas, for the radiation, the gas is just the temperature, and here you have P by this, so you just multiply. This is the reason here you have a mixed change, because here you have the sum. Here is derived the temperature, so the 4 goes here, here is the pressure just enter 1/3. The other part came from this one, okay. 84 the 1 over density, and do all the calculation considering the beta value you get for the 3 parameters before this value change. Beta 1 and beta 0, all the three have the same value, but actually in Y, if you have only gas with 3 are 5 and R is the adiabatic coefficient. In the case of pure radiation, the adiabatic coefficient goes to infinity because it doesn't, you see here, gamma goes with the its capacity and pressure constant and the volume constant, and for radiation this value goes to infinity. So are not more equal, also they are equal among them, are not more equal to the adiabatic coefficient. Oh, okay, I think this I will this so. But you see a relation tan energy connected with the two. So on the avian, if the pressure on gas is more important, it's of like a normal gas, so relativistic gas. So, okay, since that we are, there is no one hearing me, I'll stop here and for tomorrow. And because I wanted to reaffirm some part about the generosity. It's an important point. See you tomorrow.